Thank you so much for joining us at the FreeFlyer Expo today. We are very excited to tell you all about FreeFlyer 7.8 and what we've got in store. What I want to do is just kind of walk through our technology today. Thanks for joining us on Zoom. You'll have access to the Q&A feature. This will allow you to ask questions of all of our panelists and presenters today. Our sales team will be acting as the moderators for those questions, and we'll present them to the speakers at the end of each talk. So you don't need to worry about interrupting their train of thought or anything like that. We'll handle all of those things. So as soon as you have a question, please ask it. If it is very involved or particular to maybe your specific mission plan, we will follow up after the call with that answer. So please ask away, and thanks for joining us today. Just a brief overview of our agenda. We'll be starting with Nate McCoun, head of our support team, to walk through the new features in FreeFlyer 7.8. Then we'll hear from the University of Illinois in Urbana-Champaign. Michael Harrigan will be speaking to us about integrating FlatSat with FreeFlyer. One of our developers, Luke, will be speaking about optimal control. Clark Newman from the NASA Gateway team will be talking about estimating drag coefficient from TLEs for reentry. Michael Volley, another one of our developers, will be talking about custom measurements, the new feature for orbit determination in FreeFlyer 7.8. Brian McCarthy, also from the NASA Houston Gateway team, will be talking about transitioning cislunar trajectories between fidelities of models. Scott Lowe from our AI Labs team will be introducing the kernel system for us. Irfan Rashed from CASTE will be talking about autonomous constellations for LEO and LLO and how FreeFlyer relates to all that. If you have to leave and come back, you're welcome to do so. The talk will start on the top of the hour, the top of the half hour. If you leave early, you will be asked to do a survey. We ask that you please complete that so that we can get information about how your experience was today. Everybody will remain muted. We ask you to use the Q&A function. We will be recording this talk and we'll be uploading it to YouTube for future notes. So don't take notes and scribble too hard. We will be posting all this for later consumption, so you can share it with all your friends, obviously. All right, and with that, I want to hand it over to Nate.
Thank you, Michael. I'm going to go ahead and steal screen share from you. All right, welcome everybody to the FreeFlyer Expo Winter 2022. Appreciate the introduction, Michael. My name is Nate McCoun. I'll be kicking the expo off with what's new in FreeFlyer 7.8. So without further ado, we'll go ahead and introduce our three major headlining features. The first one we'll talk about today is going to be collocation-based optimal control. We'll then introduce custom observations and orbit determination. And finally, we'll talk about interplanetary and xGEO propagation enhancements, which were made in FreeFlyer 7.8. As Michael mentioned in the agenda, we do have a few more in-depth presentations later today. Luke will be presenting at 2 o'clock on collocation-based optimal control, a specific GTO to GEO use case. And Michael Volley will be talking about TDOA, FDOA custom measurements at 3 o'clock on custom observations and orbit determination. The first thing I want to introduce are a few of the sample mission plans which we've added to FreeFlyer 7.8, 12 in total, a few of which we'll cover a little bit right now and some a bit more in depth later, considering their headlining features. We've added them in 4 different sections of our sample mission plan folders. You can see here coverage and contact analysis, maneuvering and targeting, optimization, and orbit determination. In the coverage and contact analysis folder, we've added a custom coordinate system sample mission plan, which demonstrates the creation of 3 custom coordinate systems centered on a spacecraft. The first being a local vertical, local horizontal, or LVLH coordinate system, which is used to visualize the default spacecraft reference frame in FreeFlyer. A sun pointing coordinate system, which is used to orient the spacecraft such that it's constantly pointing towards the sun. And a body coordinate system, or BCS, which is used to visualize the spacecraft's divergence from the neutral LVLH state as it points towards the sun. In the maneuvering and targeting folder, we've added 3 new sample mission plans, the first being the GEO rendezvous sample mission plan, which you can see here on the right side of your screen. This mission plan demonstrates a possible maneuver sequence to place a coplanar near neighbor's chaser satellite, known as the Deputy, into a natural circumnavigation arrangement with a geosynchronous target satellite chief. And the circumnavigation injection maneuver components are calculated using FreeFlyer's built-in relative motion utilities. The second mission plan in this folder is going to be the target equally spaced formation sample mission plan. And this mission plan demonstrates the advantage of initializing an equally spaced formation around a circular orbit using J2 Bryrodane elements as opposed to Keplerian elements. It starts by initializing a formation of spacecraft using Keplerian elements, propagates for some duration, and outputs the track drift. So the other mission plans, the first one is the target launch asymptote right ascension. We'll talk more about that when we get into the xGEO enhancements made in 7.8. The optimization mission plans will go more in depth with the optimal control enhancements. And finally, the orbit determination mission plans we'll be talking more about at the end when we talk about custom observations in FreeFlyer. So let's go ahead and jump into the next thing, which is the collocation-based optimal control, the main headlining feature of FreeFlyer 7.8. Optimal control in FreeFlyer 7.8 will increase fidelity for users doing trajectory optimization that involves propulsion elements, specifically or especially low thrust propulsion elements. Segmented trajectory arcs and collocation will greatly improve convergence for nearly all trajectory optimization problems in FreeFlyer, regardless of whether a propulsion element is modeled or not. These new features integrate directly with existing optimization functionality to easily implement complicated problems with simple FreeFlyer script solutions. The main new object is going to be the trajectory phase object, and using this object, bounds and constraints can be added to the optimization problem to reflect real-world limits when optimizing your objective function. There are 3 control models available for use, which we'll talk more about in the next few slides. They're the ballistic control model, the simple thruster, and an ideal solar sail control model. These new features employ a third-order Lagrange Gauss-Lobato LGL collocation algorithm to efficiently optimize a trajectory in parallel rather than one step at a time via integration. And a major component here is that collocation ensures that the approximating collocation polynomial agrees with the system dynamics, including its force model. So let's talk about how to do this in script. So the first thing when working with the new optimal control enhancements added to FreeFlyer 7.8 is to define your problem. And when you're defining your problem, there are 3 subcomponents here. The first being to create and initialize a trajectory phase object, similar to how you would do with any other object in FreeFlyer. We start by initializing a trajectory phase object and give it a name. So here we're defining this trajectory phase as phase. And then what we'll do next is actually initialize this trajectory phase object through the collocation options properties. So through these properties, users have the ability to edit properties that pertain specifically to the collocation dynamical solver, including the force model. So here you'll see that we're defining the trajectory phase as force model, turning off the the force applied by the sun, the moon, and drag. And the next thing we'll do is that we'll go ahead and configure our force model, or I'm sorry, control model. So as I mentioned in the previous slide, there are 3 control models available to use with the new trajectory phase object, the first being ballistic. Ballistic control model allows users to model a trajectory segment with no control. The example you're seeing in this script here is a simple thruster. So we've changed the control model.control type property, set that equal to 1 to now use a simple thruster. The simple thruster control model allows users to model continuous thrust maneuvers using a thruster of constant ISP and maximum thrust. Through the control model, we have a few additional options to actually edit the simple thruster control model we'll be using the simple thruster options. So here we're setting a maximum thrust of 5 newtons, a constant ISP of 800 seconds, and a duty cycle of 1. You have these additional properties available for an ideal solar sail control model as well, except for these allow you to have full control over the sail parameters such as the area and efficiency factor. So as you can see, we have the simple thruster options, and then you would also have available to you the ideal solar sail options. Also through the control model, you have the ability to add shadow constraints using the add shadowing body method. When shadowing bodies are present and the control type is set to simple thruster, constraints will be applied which prevent thrust when the path of the trajectory phase is shadowed by at least one of the shadowing bodies. Similarly, when shadowing bodies are present in your control model type is ideal solar sail, the solar sail will produce no thrust when the path of the trajectory phase is shadowed by at least one of those shadowing bodies. Continuing with defining our problem, the next thing we want to do is create an initial guess. When we're creating an initial guess, we need to start by setting up our spacecraft. We'll then add nodes. You have the ability to resample nodes. You can also set bounds and lock variables. So let's go ahead and take a look at how this script is set up. Similar to the trajectory phase, we're going to start by configuring our spacecraft and its force model. So here you can see that we're defining our spacecraft called SC. We're going to use an alias so that we don't have to typecast our force model each time. We're going to be setting our force model up to be the exact same as which we set up our trajectory phase in step 1. So turning off the sun, moon, and drag, etc. But we're also going to configure our initial spacecraft parameters, such as its mass with 1,000 kilograms. We're going to set up some Keplerian orbital elements. This is going to start at a 10,000 kilometer semi-major axis, a relatively circular orbit with an eccentricity of 0.0001, an inclination of 10, and a true anomaly of 0 degrees. So that's just our initial conditions for our spacecraft. Now we're going to go ahead and add nodes. Nodes represent the discretized path of the trajectory phase, and nodes are going to be added to the underlying trajectory nodes of a trajectory phase object through either the add node or add nodes methods. In this case, we're going to propagate the spacecraft for one period, adding a node at each step. So if you think about the default spacecraft in FreeFlyer, it starts with a default step size of 300 seconds. So while we're propagating our spacecraft for one period, we're going to be adding nodes at each step. So we'd have a node spaced out every 300 seconds in this case. The next thing you'll see is that we are going to resample nodes. So resampling nodes in this case, we're going to create 50 uniform spaced node points. We do this by using the resample nodes method call. And in this case, we're just using one argument for 50. And this would just set up a uniform spacing of node points in time. There are other overloads which allow you to include barriers. So you can use independent uniform distributions with your user-defined barriers. An example of this might be placing 20 nodes in the first 30% of your trajectory and 10 nodes in the last 70% of your trajectory, or you can also concentrate nodes at the start or end of your trajectory. To further constrain the problem, users can set bounds on variables associated with the trajectory phase, and you can do this through a number of useful methods. These variables can be locked at the first or last node of the trajectory phase, or along the entire path of the trajectory phase with a past range and/or index. Some examples of this may include setting bounds for position, velocity, mass, time of flight, or epoch. And then at the bottom here, you can see examples where we're using the trajectory phase and locking variables. And in this case, we're locking two variables. We're locking the epoch at the first node through the lock epoch method call. And then we're also locking the mass at the last node point to be 500 kilograms through the lock mass method call. You could also lock the position, velocity, epoch, time of flight, or control variables, but here we're just getting an introduction to a few of these different methods. So now we've defined our problem. The next thing we want to do is we want to load our optimization engine. There are two steps when doing this. The first is to add trajectory phases to the optimizer. So you can see in the code snippet here, the commented section above is just where we're defining the problem. The next part is where we're actually going to add those trajectory phases to the optimizer. In this example, we've created or initialized two trajectory phases, phase Earth and phase Mars. You then initialize your optimizer. So this is the object that has existed since FreeFlyer 7.6. You have optimizer, we're initializing it called opt. And then we'll use the add trajectory phase method call to actually add those phases which we've created and define the problem with to that optimizer. Next, you want to define phase links and add general constraints. So constraints are used in an optimization process to define conditions which must be met in order for the solution produced by the optimizer object to be considered feasible. And when you're solving an optimization problem that includes multiple trajectory phase objects that are intended to be continuous, so in our case, we're thinking of, we have a phase Earth and a phase Mars. We can think of this as an initial configuration for an Earth to Mars low thrust transfer. You want to link those two phases together across position, velocity, mass, and epoch so that they're continuous. And we do this through the optimizer.addPhaseLink method call. You can see we have two overloads shown here. The first overload, we are linking the last node of phase Earth with the first node of phase Mars. The second overload is demonstrating the same behavior, but it's a little bit more explicit, where we're linking the last node again of phase Earth to the first node of phase Mars, creating that continuous trajectory arc. We won't go too in depth on the constraints, considering they are a part of the enhancements added to FreeFlyer 7.6, but you can see here how we would add a constraint block for initial position and velocity, as well as final position and velocity through the op.addConstraint block method call. So we've defined our problem, we've loaded the optimization engine, we've added our trajectory phases to the optimizer, and we've defined any phase links if we're trying to create a continuous trajectory arc. We've added our general constraints, and now we need to go ahead and create the evaluation loop. So once defined, the problem must be loaded into a third-party optimization library. FreeFlyer includes built-in support for IPOpt and NLOpt. We also support SNOpt, but as a user, you must have an SNOpt license, provide the path to the SNOpt shared file. If you want more information on these various third-party optimization engines, we do have a full guide in the FreeFlyer help file. It can be found under optimization engines. So the process of creating an evaluation loop and retrieving the best solution is going to be summarized here in these bullet points here on the left, but you can find more detail on each of these sub-steps on the using the optimizer guide. These steps include loop condition. So if we look at the script here on the right, we have a while loop, and we're saying while our optimizer has not converged, we're going to do these things. We're going to restore our saved objects. We're going to update and retrieve state variables, perform any analysis, update constraints, provide any known derivatives, minimize or maximize the objective function, solve for our constraints, and most importantly, generate some output. So in this example here, we're saying while our optimizer is not converged, let's report the current state variable, constraints, and objective function values on each nominal evaluation. And then once we get a feasible solution, let's report the best solution parameters so far. So this would be the best state variable values, constraint values, as well as the best objective function values. So we've created our evaluation loop. We've retrieved our best solution. Now we want to actually visualize our solution. So the trajectory phase object allows users to visualize nodes, paths, and control vectors in 3D views. Nodes are going to be these data are the points that we were talking about. Paths would be the entire trajectory arc. And then your control vectors, you can see a good example in the bottom left here. And they can all be colored 3 different ways. The first is going to be a constant color. So if you wanted all your nodes, your paths, or your control vectors to be, say, red or green, you can do that. You can also color them a little bit more dynamically using either the collocation defect error or the dynamical error. So if you're going to use the collocation defect error, these node points or paths or control vectors would be color-coded according to the collocation defect error, where it would be a gradient from red, orange, yellow, and green, red indicating collocation defect error, and green indicating collocation defect integrity. The other option is dynamical error, where these points would be color-coded according to dynamical error, using that same gradient of red, orange, yellow, and green, red indicating collocation defect error, and green indicating collocation defect integrity. So in script, it's pretty easy to get these visuals put in place. So you can see we're initializing our trajectory object, our trajectory phase object, calling it phase. And we'll first look at the nodes. So if we wanted to draw the nodes in our 3D view, we would say phase, draw node, and just set that property equal to 1. You can see by default, we have these circles. You could change that tick type to be circle, X, cross, whatever option you see fit. You could increase or decrease that tick mark size. And then for the actual coloring, this is where the node color mode property comes into play. We've set this property equal to 1 for nodes in this case, where we're coloring based on that collocation defect error. The same goes for paths. If we wanted to turn paths on, we simply say draw path, set that equal to 1. And then for our path color mode, we're changing this property set equal to 2. So then we would be basing that on the dynamical error. Finally, for control vectors, you have the same properties available to you. We're going to say draw control vector, set that equal to 1. And then for the color mode, in this case, we've set that equal to 0, and that would be a constant color. So that's, you see it white in the visual on the left. And then finally, you could set a maximum length for that control vector. And in this case, we've set it equal to 100,000 kilometers. And this example that I keep mentioning over here on the left is from our sample mission plan, Earth to L1 solar sail. And we'll talk more about that in depth in the next slide. All right. So we'll talk more about the optimal control sample mission plans we have available. The first one that we have here is the control acceleration integration sample mission plan. So this demonstrates solving ordinary differential equations, or ODEs, using collocation and numerical integration. So I'm going to go back to the beginning here for a second, and we'll see the optimizer doing its magic. We're going to see these node points changing based on the collocation defect error. So once we get to an optimal solution, they're in that green state. And then this red you're seeing going around, that's the spacecraft, which is being propagated with an integrator. In this mission plan, you'll see the difference between solving your ODE using the new collocation for the optimal control enhancements versus using a numerical integrator, where you will finally see the range difference at the end of that propagation. The next one we'll see here is going to be the one that was visual on the last slide as well. It's Earth to L1 solar sail. And this demonstrates using 3 different trajectory phase objects to optimize the time of flight from Earth to the Earth-Sun L1 point. So again, we're coloring these points based on the collocation error. As this maximum feasibility goes to 0, we can see those collocation points getting, our node points turning green, and we found our optimal solution. The next one we have is the Earth to Mars continuous thrust. This demonstrates FreeFlyer's capability to perform a continuous thrust transfer from Earth to Mars using the trajectory phase object. And in this case, we're solving for the minimal time of flight. Next, we have the high amplitude halo orbit. So this demonstrates configuring a high amplitude halo orbit around the moon using a trajectory phase object. Once we've found our optimal solution, we'll visualize this for 1 revolution just to get an idea of how this orbit would look. So we'll let this get all the way around for 1 rev. And we'll cut to the final one, which I will want to pause. This one's pretty quick. Thanks to Luke for making everything so fast with optimal control. So this is the mesh refinement sample mission plan. This demonstrates the refined mesh method to optimize node placements for a sun-centered orbit. The refined mesh method inserts trajectory nodes in areas where the trajectory phase, where the dynamical errors defect are detected, and trajectory nodes will also be removed in areas where dynamical accuracy is excessive. If no dynamical error is detected that violates the relative error tolerance, then no nodes will be added. So if we take a look at our original guess, or initial guess, you can see we have concentrated nodes towards the end of our initial guess, very sparse node points at the beginning. And so what FreeFlyer is going to do using this refined mesh is it's going to add node points where that dynamical error is detected. It'll remove it where we have excessive, or I'm sorry, it's going to remove the nodes where dynamical accuracy is excessive. So we can expect that it'll remove some node points up here at the end of our trajectory and add some points at the beginning. And it does it in 5 iterations where you finally get your optimal solution. If we flash back to the first slide, you may have noticed that there was 6 sample mission plans that talked through 5. I'm going to let Luke at 2 o'clock talk through the GTO to GEO sample mission plan in more depth. So be sure to tune in for that. The next thing we'll talk about is custom observations and orbit determination. So custom observations in FreeFlyer 7.8 added the ability to let users define their own measurement models in script. It allows users to leverage the flight-proven nature of FreeFlyer's propagation, covariance, process noise, and estimation models with new and/or different measurement models that are non-standard. Excuse me. Supported by all estimators in FreeFlyer, your extended Kalman filter, your unscented Kalman filter, your square root information filter, and batch least squares. And it processes the user-provided partial derivatives, pre- and post-update computed values to progress the estimator. Be sure at 3 o'clock to tune into Michael Volley's talk for an example on doing TDOA, FDOA custom measurements in FreeFlyer 7.8. And the last thing we'll talk about today is the interplanetary and xGEO propagation enhancements, which were made to FreeFlyer 7.8. So new astrodynamic values for planning Lagrange point missions and hyperbolic trajectories are now available for use. You can see the examples here below: apoapsis declination, right ascension, and vector. You have hyperbolic excess velocity vector, launch asymptote declination, and right ascension. And we've built out an example sample mission plan, which is showing here on the right. This mission plan demonstrates how to target the launch asymptote right ascension, RLA, for an interplanetary transfer. So it starts with a near circular parking orbit around Earth, and then a transfer orbit insertion burn is performed, varying the delta V right ascension of the ascending node and argument of perigee to achieve the desired RLA. And then the RLA, so I guess a little more in depth on RLA, is the equatorial east longitude from the vernal equinox. And it can be used when designing these departure trajectories to match the mission required outgoing V infinity vector to the specified launch site location. So that's a lot of information, but we don't like to leave you out there to dry. So learning to use these new features in FreeFlyer 7.8, there are obviously a handful of resources ready for you. You can check out the release notes for in-depth information on all the enhancements made. You can find these in the appendix of the FreeFlyer help file. Also found in the FreeFlyer 7.8 help file are new guides. We have a guide for optimal control, which can be found under the optimization subsection. And you can also find a page on custom observations in the orbit determination guide. It's going to be under the tracking data, observations and measurements, and you'll see custom observations available to you there. Also, along with these new guides in the help file, we have all the sample mission plans, which we just walked through. So the 12 new sample mission plans based on these new enhancements. And then in the future, if you'd like to be a beta tester for FreeFlyer 7.9 or beyond, please reach out to our technical support team, and we'd be happy to coordinate with our product manager to get you set up. This was a big factor in our FreeFlyer 7.8 release. We had a lot of users using these new enhancements throughout the summer. And now they've got their hands, had their hands on these new enhancements, and they're ready to get running as soon as we officially release with FreeFlyer 7.8. So I think that brings me to the end of my time. Are there any questions in the chat, Michael?
There are some questions. However, we're at the end of our time, so we will answer those questions offline. A lot of the questions are related to optimal control, and so we will throw those to Luke later in the day.